Dear students, today I am giving the 6th video on Topology 2. Last class we had discussed about T0, T1 and T2 spaces in detail, and given us a homework that is how to prove the product of T0 spaces is again a T0 space. And the product space we are taking of T0 spaces, whether the product is again a T0 space or not. I think you have done it, otherwise you can discuss it now. In a similar way, you can prove the product of T1 spaces is again a T1 space. Product of T2 spaces is again a T2 space. That's what the first theorem. We can prove it here. Theorem for each I equals 0, 1, 2, the product of Ti spaces is a Ti space. Proof we can see. We are taking the collection of T0 space, that is x alpha to alpha index set to be a collection of T0 spaces. And product space capital X equal to pi x alpha. Take tau as the product of topology on x. It prove that x twice again a T0 space. Taking 2 points there, that are distinct points x alpha in index set, and y alpha index set. We two distinct points in x. Then definitely x beta is not equal to y beta for some beta in index set. So we are having 2 points x beta, y beta in x beta, and x beta is a T0 space. So by the definition of T0 space, the x is u beta open set u beta in tau beta, such that this x beta, small x beta is in u beta and y beta is not in u beta. You take capital U as pi beta inverse of u beta, where pi beta is the projection mapping. Pi beta inverse of u beta. Then u is clearly open in x2. Also, small x is in u and y is not in u. That means x2 is a T0 space. In a similar way, we can take the second case. Let x alpha to alpha in index set be a collection of T1 spaces. Put x equal to pi x alpha product space. Let tau be the product of polygon x. To prove that x2 is a T1 space. Taking 2 distinct points at x alpha in index set, and y alpha index set be 2 distinct points at capital X. Then x beta is not equal to y beta for some beta in index set. That is x beta, y beta 2 points in x beta, and x beta is a T1 space now. The x is u beta in tau beta, and v beta in tau beta such that x beta is in u beta, y beta is not in u beta, and y beta is in v beta, x beta is not in v beta. Take capital U as pi beta inverse of u beta, capital V as pi beta inverse of u beta, where y beta is the projection mapping. Then u and v are open in x2. Also x in u, y not in u, and y in v, x not in v. This implies x2 is a T1 space. This implies x2 is a T1 space. Or we are getting the product space is again a T1 space. In a similar way, we can prove that product of T2 spaces is again a T2 space. That I can do in the same way. Next theorem we can discuss. Let x2 be a topological space and yu be a Hausdorff space. Let fg, f and g, two functions from x to y, be continuous functions. If f and g agree on a dense subset of x, then f equal to g. If f and g agree on a dense subset of capital X, then f equal to g. You can see the proof of it. Let a capital D be a dense subset of x, and let fx equal to gx for all x in D. And because D is a dense subset, and on D, that is for every x in D, f of x equal to g, that is f and g agree on D. That is what the meaning. Let D be a dense subset of x, and let fx equal to gx for all x in D. You can read it properly. because x to be a topology space, yu be a Hausdorff space. Fg from x to y be continuous functions. If f and g agree on a dense subset x, that part we are discussing. Deviate dense subset x, let fx equal to gx for all x in D. That f and g agree on D. What we have to prove? F equal to g we have to prove. That is fx equal to gx for every x in capital X. In that way we have to prove. Not only for the case of capital D, even instead we are discussing the whole space, that is fx equal to g. F and g agree on D in the sense f and g agree on capital X. That's what we have to prove. Proof that deviate subset x and that fx equal gx for all x in D, to prove that fx equal gx for every x in X. That is to prove that fx equal gx for all x in capital X minus D, because that part is already done for D. So x minus D part, that there you have to prove that fx equal to gx. If possible, assume that or assume that it is not true. That is, assume there exists some x in x minus D such that fx not equal to gx. Now fx gx in capital Y, and y is Hausdorff, of course. Then by the definition of the Hausdorff space, there exists v1 v2 in U such that v1 intersection v2 equal to phi disjoint, and f of x is in v1 and g of x is in v2. We call it that part, that v1 intersection v2 equal to phi as a result of 1. Then f inverse v1 and g inverse v2 are open in x term. Also small x is an element of f inverse v1 intersection g inverse v2, which is a capital U. You can call it as capital U, as U is a neighborhood of x. We have x is in small x is in capital X. What is x? Let's take d bar, because d is dense in x. So d bar, x equal to d bar. We have every neighborhood of small x intersects capital D. In particular, U intersection D not equal to phi. If U intersection D equal to set x not equal to phi, you have to take. So you take in particular U intersection D equal to set x, singleton set x, then x is in D. This implies f of x equal to gx. It's a contradiction to our assumption. Suppose there x is z in x such that z not equal to x, and z is in U intersection D. That means z is in U and z is in D, or z is in f inverse v1 intersection g inverse v2, and fz equal to gz. This implies fz is in v1 and gz is in v2, and fz equal to gz. What does it mean? That is v1 intersection v2 is not equal to phi, which contradicts the result 1. What we have already mentioned, the result 1, as v1 and v2 are disjoint. Hence, f of x equal to gx for every x in X. Next theorem, let X be a topological space and let D be a dense subset of capital X. Let YU be a Hausdorff space. Let F from D to D subspace topology, that is D and topology is to suffix D to YU. Y is a Hausdorff space, be a continuous function, then f has at most one continuous extension on X. If possible, you take two continuous extensions, that is f, g and h. Suppose g and h from x to y be two continuous extensions of f, then g restricted to capital D. What is that? It's f. Similarly, h restricted to capital D. It's again f, because they are continuous extensions of f. So on the space D, they agree, or g of x equal to h of x equal to f of x for every x in D, where D is a dense subset of x. Then by the previous theorem, the theorem is now we have proved gx equal to hx for every x in x, or g equal to h, hence f has at most one continuous extension on capital X. Next definition, that is what retract. A subset capital A of a topological space x to y is a retract of capital X, provided that there is a continuous function gamma from x to capital A such that gamma of A equal to A for every A in capital A. Subset A of a topological space x to y is a retract of capital X, provided that there is a continuous function gamma from x to A such that gamma of A equal to A for every A in A. One example you can see, consider 0, 1, close interval 0, 1, subset or equal to R, and gamma from, or you define gamma from R to 0, 1 by gamma of x equal to 0 if x less than 0, equal to x if 0 less than or equal to x less than 1, equal to 1 if x greater than or equal to 1. Clearly, gamma is a continuous function, so that 0, 1, that is the subset 0, 1 is a retract of capital A. So one theorem we can discuss using the definition of retract. Let x2 and yu be topological spaces. Let capital A be a retract of capital X. Let f from A to y be a continuous function. Then f has a continuous extension capital F from x to y. You can see its proof. Suppose that A be a retract of x. You can refer the definition. Retract as when A is a retractor, that is the x is a continuous function gamma from x to A such that gamma of A equal to A for every A in A. So suppose that A be a retract of x, then by the definition there is a continuous function gamma from x to A such that gamma of A equal to A for every A in A. You can see that is x to A, gamma is from x to A, and f is from A to y. So what about the composition? F composite gamma, that is from x to y. Now f composite gamma from x to y is a continuous function, because composition of continuous functions, once again a continuous function. You take it this as capital F equal to f composite gamma, and take an element A in A, then capital F of A equal to f composite gamma of A, that is f of gamma of A, which is f of A because gamma of A equal to A for every A in capital A. That is restricting on capital A, that is capital F restricted on capital A. That is nothing but small f only. Hence f has a continuous extension capital F. Next theorem, that x to be a topological space and yu be a Oster space. Let f from x to y be a continuous function. Then the collection of ordered pairs x1, x2 is an element of x cross x satisfying. F of x1 equal to f of x2 is a closed subset of x cross x. You can see the proof of it. You take capital A as that set, given set, that is a collection x and x2 in x cross x satisfying fx1 equal to fx2 to prove that A is closed. It is sufficient to prove that x cross x minus A is open. You take an element AB, ordered pair AB in x cross x minus A. This implies AB is not in capital A, which implies f of A not equal to f of B. That is, you are getting two distinct points. Now f of A, f of B in capital Y, and yu is also. This implies the x is open such uv in u such that f of A is in E capital U, f of b is in capital V, and U intersection V equal to phi. Also f inverse U and f inverse V are open in X. Why? Because f is continuous. And we have the element AB is in f inverse capital U cross f inverse capital V. Note that f inverse U cross f inverse V is open in X cross X. What we are proving is this f inverse U cross f inverse V is subset or equal to X cross X minus A, so that we can prove that X cross X minus A is open or A is closed. You take an element x1 x2 in f inverse U cross f inverse V, that is x1 is in f inverse U and x2 is in f inverse V, which implies f of x1 is in U and f of x2 is in V. This implies f of x1 not equal to f of x2 because U intersection V is phi even we are disjoint. This implies x1 x2 is not an element of capital A, or x1 x2 is an element of x cross x minus capital A. Hence the claim. On the basis of this claim, AB is an element of f inverse U cross f inverse V, which is subset or equal to x cross x minus A. This implies x cross x minus A is open or A is closed. Next theorem. Let x2 and yu be topological spaces. Let f from x to y be an open map which is onto if x1 x2 element of x cross x satisfying fx1 equal to fx2 is closed, then y is host. You can see the proof of it, that capital A is what the given set. See collection x1 x2 in x cross x satisfying fx1 equal to fx2. Suppose that A is closed, we have to prove that yu is host. You are taking 2 points C, D and Y satisfying C not equal to D, that is C and D are distinct points. Since f from x to y is onto, the x is AB in x such that f of E equal to C and f of B equal to D. But C not equal to D, this implies A not equal to B. Thus, C not equal to D implies f of A not equal to f of B, which implies AB is not an element of capital A. This implies AB is an element of x cross x minus capital A. Since x cross x minus capital A is open, the x is open sets UV into such that AB is an element of U cross V, which is subset or equal to x cross x minus capital A. Thus, A is in U, B is in V, f of A is in f of U, and f of B is in f of V. This implies C is an element of f of U and D is an element of f of V. Or we are getting f of U and f of V both elements of U, because f is an open map. And we had to prove that f of U intersection f of V equal to phi. That is, it remains to prove that f of V intersection f of V equal to phi. If possible, assume that it is not true. That is, assume that f of U intersection f of V not equal to phi. There is at least one element, say z is f of U intersection f of V. This implies z is in f of U and z is in f of V, which implies f inverse z is in U and f inverse z is in V, which implies the ordered pair f inverse z, f inverse z, because one is in U, other one is in V. F inverse z is in U cross V, which is subset or equal to x cross x minus capital A. But f inverse z, the order pair is an element of capital A, which is a contradiction. Hence, f of U intersection f of V must be equal to phi. This implies f of, or the space yu is a Oster space. That's all about the first unit of first section of unit 2. And I am giving here 9 pages notes too. You refer the notes properly and listen the video, and any doubts means we can discuss in the next class.